Okay, so hi, I'm Sanja, and this is joint work with Tomasz Gogacz from University of Warsaw and Magdalena, Ortiz, and Mantas Simkus from TU Wien. And if the title didn't give it away, I want to share with you a technique for rewriting ALCHOIF with closed predicates into a variant of Datalog, and this variant is Datalog with negation under the ANSYS set semantics. Now, when we were developing this translation, we had two goals in mind. First, keep it small, so keep it polynomial. And the second is keep it data independent. And before I tell you about how we did this, you might want to ask why. And here is the simple answer. So to understand relative expressiveness and close complexity gaps. However, I want to note that, I want to note that both the description logic community and the ANSYS set community have long been interested in exploring relationships between description logics and ANSYS set programming. And we want to contribute actually to this conversation by considering non-monotonic logics and those with closed predicates, but this makes it tricky. And why does it make it tricky? Well, because closed predicates add non-monotonicity, and also because this combination of inverses, nominals, and functionality is already problematic in itself. And this causes the increase in complexity from exponential time to non-deterministic exponential time, and also the loss of forest model property. So the usual techniques don't work. And when I say the usual techniques, I mean some type of resolution-based calculus or type elimination algorithm. Now, as far as I understand, there is limited research on resolution-based calculi for non-monotonic logics. So we moved away from that very quickly. And then type elimination usually kind of relies on these convenient properties that we don't have, like forest model property. So we looked into the literature and we saw, okay, the only complexity optimal algorithms that we see for ALCHOIF here are based on integer programming. So why don't we just try to characterize satisfiability of ALCHOIF with closed predicates as a system of linear inequalities, and then we will see how we can craft a Datalog program to generate and solve these inequalities. So if you've never seen ALCHOIF before, or you may not remember what it looks like, here it is. So this is the T box of this shape. Then we have the A box, and the knowledge base is just T box plus A box plus some set of closed predicates. And if you're not a description logic person, then maybe you want to see this in first order logic, and then you kind of can guess what the models look like. So just first order interpretations that satisfy this theory, this A box, and interpret all the closed predicates exactly as given by the data. Now we also have a standard name assumption, which just means that constants are interpreted as themselves. I think Datalog doesn't really need an introduction, so I just want to mention that we are dealing with rules of this kind. We have also facts, and programs are just rules plus facts. That's all. And this brings me to the first point of my presentation, where I want to show you how we can characterize ALCHOIF satisfiability using integer programming. And this is adapted from a paper of Gogacz and his colleagues that was published in ECAI this year. So one of the main concepts that I want you to understand today are the concepts of tiles. So you probably all know about types. This is just a description of the main elements in terms of which concept names it participates in and possibly which nominals it represents. Now, a tile is a compact description of some domain, and it is, in addition to this information that is provided by the type, we also store the information that is provided, the information about the kind of neighbors that this element has. So, and these neighbors are described by their types of their own, and then the kind of roles that connect them to the main element. So tiles are not just arbitrary descriptions. They need to satisfy some conditions that ensure that these descriptions are consistent with the statements in the knowledge base. And you can see these tiles as building blocks for constructing models. So if you see your model as a puzzle, you can see a tile as a puzzle piece. So here is what the conditions look like, but don't panic. I don't want you and don't expect you to read this slide. I will just try to explain it briefly here. So we have a tile from the previous slides, and let's say we have this kind of axiom in the T box. So every B has an S neighbor that is a C. So, okay, here's our element. In its type, it's a B. So then it has to have an S link to some element that has a C in its type. And you can do this for all different kinds of T-box axioms, and you also need to do this to account for the A box. But what I want to stress is that we only really encode the necessary information. So we don't just go encoding the whole A box into the tiles, because this is going to make them blow up. So they're not going to, their size is not going to be independent from the A box. So we only really keep track of those neighbors whose existence is implied by existential axioms. Cool, so now that we have the tiles, I will tell you what mosaics are. And mosaics are just functions that tell you for each tile how many elements that fit the description of this tile you need to build the model. And they also satisfy some conditions to ensure that actually we're able to put these elements together and like connect them and get a model. So this, in like plain words, these conditions are as follows. So there's at least one element. Each nominal corresponds to exactly one element. Each element can find required neighbors, so we can connect them to obtain the whole puzzle. And then functionality assertions and universal axioms will be respected. Now, this is what it formally looks like. And once again, I don't want you to read this. I just want to show it to you. And if you're interested, you could have a look at the paper. And this brings me to the first main point of this presentation, is that a knowledge base is satisfiable if and only if there exists a mosaic for this knowledge base. And then additionally, the A box needs to satisfy these two conditions that can be in plain words explained as, okay, so if we take our A box and we close it under the role inclusions, then we will not get anything new in the closed predicates, and we will still satisfy functionality constraints. So it seems like the main part here is to try to figure out how we can decide the existence of mosaics for the knowledge base. And this can be done using enriched systems. So enriched systems are just systems of linear integer inequalities. And we have some implications that must hold on the side. And the conditions that we place on mosaics actually define an enriched system for a knowledge base. So there is an enriched system that corresponds to the knowledge base, and the solutions to this enriched system over natural numbers that are extended with some constant to represent infinity are actually the mosaics for the knowledge base. So we get, in the view of previous theorem, that the knowledge base is satisfiable if and only if this enriched system has a solution, and then the knowledge base satisfies those two conditions I told you about. Perfect, so now we can see how we can actually encode these enriched systems using Datalog, and then how we can solve them. So here is the general plan, the general picture. So we're given a T box and a set of predicates, and we are trying to kind of come up with this program. And even though ancestor programming doesn't really work like this, you could still think of this as two separate components. And this first component is the component that generates the system. So it takes an A box as an input, and then it checks whether this A box satisfies those two conditions. And if it does, then as its answer set, it has a relational representation of this enriched system for the knowledge base. And this representation is done as follows. So we need some relations that store the constants over the constants that occur in the A box, and we need a linear order over them. Then we need relations that store variables, inequalities, and implication, and they are encoded as strings over these constants. And then an additional relations store which variables and which constants occur where in which inequalities. So when we have this, then this system is passed to the second component, and this component just looks at it and tries to solve it. So the answer sets to this system, to this program, are the solutions to the enriched system. And actually the answer set to this program are the answer set to the whole program. So you now have the idea of the general plan. So I can tell you a little bit more about how we do the generating part. So the first thing is we collect the constants from the A box and we guess a linear order. And we need these in order to be able to encode our variables, inequalities, and implications. So the second thing is, if you think back, our variables are just tiles, right? So we need to somehow encode the tiles. And first we encode the candidate tiles, which is just like all the tiles if we didn't care about those conditions. And tiles consist of a type and then a set of neighbors. And these neighbors are again specified by their type and a set of roles that connect them to the element. And this I will call role type for now. So role types are very easy and straightforward to encode. You just assume an enumeration of roles from 1 to L, and then you have a bit vector where each position, if it's 0, it indicates that the role is out of the set, and 1 that it's in. This is very standard. Now, for the types, the problem is that the types kind of depend. So the number of different types kind of depends on the size of the A box, polynomially, but it still depends on it. So in order to keep these arities fixed in terms of the T box, if we consider T box fixed, we can encode the type as a bit vector of length K first, where this is just an enumeration of concept names. So again, similar as the role type, but then we reserve the last position. And here we actually allow constants from the A box to occur to denote which nominal, if any, occurs in this type. And once you have this kind of representation, then encoding candidate tiles is very straightforward. I just want to mention that this N here means the size of the T box, or actually the number of existential axioms. Now, the next thing is to eliminate the invalid candidates, so the tiles that violate the conditions or the duplicates. And we just go through the conditions. We can straightforwardly translate them into the rules, and then those that violate the conditions we store in invalid tile relation here, and then the remaining candidates are the proper tiles, and this makes the variables of our systems. Now we can compute the enriched system, so we have to have some sort of convention of how different inequalities and implications are encoded, and for this I invite you to look at the paper. But once we have this, then we can just go through the system and say, okay, this variable belongs to this inequality on the right-hand side, left-hand side, and so on. And when we have the encoding of the enriched system, we just need to check whether the A box respects those two conditions. And if yes, then the answer sets of this program here correspond to the enriched system for the knowledge base. And this is then passed to the solving part. Now, the solving part is just a guess and check program. So it guesses a value for every variable, finite or infinite, and then checks whether the guess satisfies all inequalities and implications. And you might wonder, okay, where's the catch? So what values should we really guess for these variables? There are infinitely many possibilities. And thankfully, there is this famous integer programming result that extends to enriched systems as well, and says, well, actually, you can only focus on those solutions where finite values are bounded by this function here. So no need to fret. But actually, maybe there is a little bit of a need to fret because those values are doubly exponential. So what do we do? How do we keep them polynomial? Well, we need a smart encoding. And I told you that variables, inequalities, and implications are encoded as strings over, so now assume D different constants. So this comes from the A box of fixed length. So we know what the size of our system is. And then we can do some simple math, some calculation, and say, okay, so actually our values will not exceed this value here. So this means that if we want to encode it as a bit vector, we would need this many bits. Now you can see we need exponentially many bits. And even the base here is actually relating to the size of the data. So this is not good. So what do? Well, actually, we encode the addresses of these bits as strings of fixed length over the constants. And this allows us to keep the arities polynomial, even though we have exponentially many different bits. Now, the values of variables are encoded as follows. So we have a predicate that saves this kind of tuples. So, and this means in the value of the variable that is encoded in V, and that is encoded by V, the bit that is at the address A has a value 0 or 1. So you could see we basically store every bit separately. And now when we have this representation, things are again straightforward. So we guess whether a variable is set to infinity or it has a finite value. And if it is finite, then we guess it bit by bit. And once we have the guess, we need to perform the check. So we collect all the satisfied inequalities. So here it again becomes a little tricky. So, okay, inequalities that have infinite variables, this is easy. So you just look if the infinity occurs on the right-hand side. And the remaining inequalities, well, we need to compute both the left-hand side and the right-hand side and compare them. And to keep now, again, the rules polynomial, we need to do this incrementally. And we do this by iterating through all the variables and keeping the intermediate results. And we use the provided linear order to do so. After we have done this, we check whether all the inequalities are satisfied. Then with simple constraints, we can also check that all implications are satisfied. And if this is the case, then we have answer sets that correspond to the solutions of the system, the enriched system. So this brings me to the last slide. I have shown you that we can encode the satisfiability of ALCHOIF with closed predicates into Datalog. We have just seen how. Now I need to note that this construction does not necessarily preserve atomic consequences, but it can be modified very easily to do so. And if you have that, then you can also answer queries using this program. In particular, we have shown this for instance queries and a large class of safe range queries that for time purposes I will not go into here. And yeah, so because you could do a query, you can answer queries using this program. You could also transfer the data complexity bound of Datalog. So we have shown that instance queries are co-NP complete in data complexity, and this also holds for the safe range queries. So yeah, if you're interested, I invite you to look at a paper, and thank you for listening. And yeah, I'm ready for your questions.